Hey guys, welcome back. Day 31. We're going to talk about stoichiometry today, which we're actually just doing reactions. Okay? And we're going to calculate how much of each reactant makes how much product. That's our goal. All right? And that's what chemistry is. You do this, if we're making dinner, how much should I make? Right? How much reactant should I have to make how much product we need? Right? How many hamburgers do we need to make? How many hot dogs do we need to make? Or whatever you're making. Same thing. Now, we're doing chemistry, unlike baking or cooking. We're doing atoms reacting in particle ratios. However, we don't use particle rate measure scales. We use mass, right? We use mass. And so converting from grams to moles, you're going to need to use molar mass. Remember, grams times, right, 1 mole over however many grams gives you moles, right? So mass divided by molar mass gives us moles, right? And we use states. The states are important. We need to know the states of matter we're dealing with, all right? Solid, obviously, and we already talked about this, solids S, liquids the L, gas, aqueous, AQ means we're in water. So those are our state symbols. So we'll need those. Now, we're just going to do 4 examples today, or in this video, just 4 examples. And feel free to stop me right now, work through it, right? And then watch up, all right, and catch up. And then do the next one, catch up, make sure everything's right. Okay, that's very important, right? You doing it. Okay, I want you to be able to do this and come up with it. All right, first thing you have to do here for number 1 is balance the chemical reaction, right? You got a chemical reaction, and I don't see any coefficients. All right, so I'm going to take, first one, 2 sodiums. So I'm going to put 2 in front of sodium fluoride. 1 silicon, 3 oxygens. If I put a 3, let's see how we go. All right, fluorine, I have put 8 there, and then how's hydrogen? 2 and 6, 8. Good. All right. Question is, how many moles HF are needed to react with 0.3 moles of sodium silicate? So we're going to start with our 0.300 moles Na2SiO3. All right, and I encourage you to write out all the units. Okay, write out all the units. If I don't write out all the units, sometimes it doesn't work as good. I can get lost. I can not know where I'm at, especially if I look at this a month later. So now, on the bottom, moles of Na2SiO3. On top, since we're already in moles, we're going moles HF, and we're going to use our coefficients, right? HF has an 8, so that 8 goes right there. And sodium silicate here has a 1, and that 1 goes right there. And so if we do this math, I get 2.40 moles hydrofluoric acid. That's it. So in this one, we just used the mole-to-mole ratio. In the second one, we got half a mole of HF, and we want to know how many grams of sodium fluoride with hydrofluoric acid, and we have excess sodium silicate. So I have extra Na2SiO3. All right. We're going to start with 0.500 moles of HF. And the same thing now happens. Moles of HF on the bottom, moles of NaF, because that's what we're going to on top. I look at the balanced chemical equation. HF has an 8, NaF has a 2. And I would leave them like that. I wouldn't reduce it to 1 and 4. I'd leave it at 2 and 8, just because now, if you look at this in the future, you'll know exactly where the 2 and the 8 came from, which is very important. It's good record keeping. Now we're in moles of NaF, but we don't need moles of NaF. We need grams. So we have another step. 1 mole of sodium fluoride happens to weigh what? Well, sodium is 22.99 and fluorine is 19. All right, and so I get 41.99. If I do this math, I think I get 5.25 grams of sodium fluoride. All right, so that was a mole amount, mole ratio of molar mass, and mole-to-mole ratio. Last one. How many grams of sodium silicate can react with 0.8 grams of hydrofluoric acid? All right, so 0.800 grams HF. Well, what has to go on the bottom? Grams of hydrofluoric acid. All right, and we're going to go to 1 mole. We're always going to go to moles, pretty much. There may be a time in gases where we don't, but most of the time we're going to go to moles. Somehow we're going to moles. So how many grams? Well, H is 1.01. Fluorine is 19. So I get 20.01. Now we have mole ratio. Moles of HF produce how many grams, or need how many grams of, how many moles of Na2SiO3 sodium silicate. And if we look at the balanced chemical equation, again, 8 for HF, 1 for sodium silicate. And one more step, because we want grams. We gotta go to grams. So 1 mole of Na2SiO3. How many grams? We're going to use the periodic table. Sodium is 22.99. Silicon, I have 28.09. Oxygen 16. And there's 3 of them. So I get 122.07. So if I do that, I believe I get 0. Oh, I didn't change the color. 0.6610 grams of Na2SiO3. So with this, what do we have here? I have molar mass, mole ratio, and a molar mass. So we have, here is an amount, ratio, gives me an amount. That's what we're doing. That's why we do what we're doing here. Not because we want to make this confusing to you. It's just those are the ratios we use. All right. Hopefully that makes sense. Hopefully you can get this. All right, let's try the next one. Again, try it ahead of me. First thing we got to do, it's balanced. How do I know it's balanced? There are coefficients, right? So if I give you coefficients, you can assume it's balanced. All right? Barring a typo, which can happen, right? But that's what it would be, so you can go with it. Now, for this one, how many moles of O2 are needed to burn that much octane? All right, so we're going to start with 1.50 moles of C8H18. Well, what has to go on the bottom? Moles of C8H18. CH18 on top. We're looking for O2. Moles of O2. And our coefficients are 2 and 25. And that's it. So I think you get 18.8. So that's just your mole to mole ratio. Next up is, it should say many here. My apologies. There's your typo. How many grams of O2 are needed to burn 10 grams of octane? Highlighter out. How many grams of O2? Now we're mass. 10 grams of octane. So we'll start with our 10.0 grams of C8H18. Well, what has to go on the bottom? It has to be grams of C8H18. On top, 1 mole. Right, this is our molar mass. And carbon's 12.01 times 8 plus 1.01 times 18. I get 114.26. Then we need to convert this octane into oxygen. So I got moles of C8H18, moles of O2. And again, I got 2 to 25. And then what? Oh, not equals. We got another one. We got to go to grams. Going too fast, right? We got to go to grams. So 1 mole of O2 weighs 32.00 grams of O2. Now we're good. Now we're good. Now I'm thinking we're getting 35. So that's our ratio for every. Now this is the cooking ratio we see, right? 10 grams of whatever you're cooking with produces 35 grams of whatever you're going to eat. Here, right? And so if I could double the mass, if I had 20 grams of C8H18, right? So if I made this 20, this would double to 70. If I half this to 5, this would have to, what is that? 17 and a half. Right? That's just how that works. If I 10 times it, make it 100, this is 350. That's all that we're talking about, right? That's the rate, because these numbers in the middle, these ratios right here, they're not going to change. All right, here's fun. This is a fun one. Maybe. All right. Octane has a density of 0.692 grams per milliliter at 20 degrees Celsius. How many grams of O2 are required to burn 15 gallons? Woo! All right, this is going to be a little bit longer. Now, the ending, hopefully you realize the ending, once I get grams of octane, is going to look exactly like this. Those are going to be the last 3 terms. But we got to go from our 15 gallons all the way down to grams. Can it be done? Of course it can be done, because I give you everything that can be done. So 15.0 gallons of C8H18. All right, we got to go to what? So I'm in gallons. I put grams down. I'm sorry, guys. Gallons. What do we have to go to? Gallons of C8H18. What should we go to? Well, I'd probably go to liters, because I need to get to the milliliters here. 1 gallon is 3.785 liters. That would be on your conversion sheet. You don't need to know that one by heart. And then 1 liter of C8H18 is 1,000 milliliters. And then we know that 1 milliliter of C8H18 is 0.692 grams of CH18. So there we go. We're doing good here. And then it's going to look exactly like it did above, right? 114.26 grams of octane. 1 mole. And I'm almost out of space. Right? And then it's 2 moles of CH18 to 25 moles of O2. And I'm going to come down here. And then we have 1 mole of O2 is 32 grams. And I'm just going to kind of connect this. I do this math. I believe I get 1.38 times 10 to the 5th grams. O2. That's a lot of O2. D asked for how many grams of CO2. So it's the same setup. I got 15 gallons of octane. But now it's how many grams of CO2. So it's going to look exactly the same until when? Until we get to the mole ratio, right? So I'm going to have, and I'll write it a little bit more compact this time, 15.0 gallons. Gallons, that's horrible. Of CH18. And we know one gallon CH18 is 3.785 liters of CH18. And we know 1 liter of CH18 of octane is 1,000 milliliters. And then we got, same color here, 1 milliliter of octane is 0.692 grams. And then what? We have 114.26 grams. 1 mole. And then we have your mole ratio. 2 moles of CH18. But now carbon dioxide is 16. And then one more step. I put it all on the same page. 1 mole of CO2 and 12.01 plus 16 plus 16. I got 44.01. If I do that math, I believe you get 1.21 times 10 to the 5th grams of CO2. 121 kilograms. A lot of CO2. And if there was a better way, most of us, and cheaper, most of us would use something besides gasoline. I don't know if there's a better way right now. That's cheaper. And more like, yeah, it's just I don't see it. Because if it was cheaper and better, I think we'd all be doing it. But it's not cheaper and better right now. So that's what we got. We use gasoline all the time. All right, hopefully that makes sense for you guys. Oh, we don't do that. We need to move up to the next example. Speaking with cars, and this one's already balanced, right? Airbags. These things explode very fast, right? To protect us from hitting the hard materials, right? And gives you sodium azide, decomposes rapidly into sodium metal and nitrogen gas. How many moles of nitrogen are produced? By the decomposition of 1.5 moles of sodium azide. Now, hopefully you guys are doing this and are going that way. All right, hope you guys are doing this all by yourself and then using me to check. All right, so we have our 1.50 moles of NaN3. And we are going to do moles of sodium azide per moles of N2. And if we look at our coefficients, so we have a 2 on the bottom and 3 at top. Well, if I do that, looks like we get 2.25 moles of N2. Next question asked, how many grams if we have 10 grams of nitrogen gas? So how many grams of sodium azide? So I need to make 10 grams. Let's see. 10 grams of N2. Well, it looks like molar mass has to go on the bottom, grams of N2. 1 mole of N2, so that's what, 28.02. All right, now we're in moles of N2. It looks like I can go moles of N2, moles of NaN3. And if we do this, 2 on the top, 3 on the bottom. But we're not done yet, because we need to go all the way to grams. So if we look at this, 1 mole sodium azide is, I think it's 6502. All right. Doing that math, I get 15.5. Again, hopefully you're getting the same thing. Hopefully this makes sense. Last one, and I like this one. How many grams of sodium azide is your question? Are required to produce 10 cubic feet of nitrogen gas, about the size of an airbag. The gas has a density of 1.25 grams per liter. Well, this looks fun. The amount I'm starting with is 10.0 feet cubed of N2. So that's what I'm starting with. All right, and we're going to multiply what has to go on the bottom. Well, if I have feet, I'm going to have feet. So feet, and we're going to go, I would go, because I'm going to liters, right? This is me, okay? I know inches to centimeters by my without looking at it up. I can just do that off the top of my head. So I'm going to go to inches. 12 inches cubed of N2 is 1 foot cubed of N2. Right? Because it's a foot by a foot by a foot, so it's 12 inches by 12 inches by 12 inches. We have to cube them. And then I know that 1 inch cubed of N2 is 2.54 centimeters cubed of N2, right? So an inch by an inch by an inch, 2.54 centimeters, 2.54 centimeters, 2.54 centimeters. All right. And then we know, at least I think we know, 1,000 centimeters cubed of N2 is 1 liter of N2. And then 1 liter of N2 happens to be 1.25 grams of N2. And now what's it going to look like? The same 3 terms up here, right? We know that there are 28.02 grams of N2, 1 mole of N2. And we're going to come down here on the bottom. So we're just going to do that because I don't have the space. Sorry about that. On the bottom is going to be, we'll use the pink again, moles N2, so 3 moles N2, and 2 moles NaN3. But we're not done. We need one more. We need mass. All right, so 1 mole of NaN3 is 6502 grams. And if I do this, I think I get 548 grams. Which is not that, it's more than a pound, but not much more than a pound. Maybe a pound and a quarter. I don't know. We'd have to convert it. But not much. So that's that one. All right. One more problem. And then we're done. So hopefully, again, this one's balanced already for you. Try it. Please try it and then come back and make sure it's right. So we have nitroglycerin decomposing. We got 2 milliliters, it looks like. All right, 2 milliliters of nitroglycerin gives you a density. And to detonate it, how many total moles of gas are produced? Well, we need gas. So there's a G, and there's a G. So it's the 12, it's the 6, and the 1. That shouldn't be a 1, I don't think. Let's double check that. 4 times 9. Yeah, that's only, yeah. That should actually be a 13. And I'll use blue. There should be a 13 there. No, I don't want to do that. I want to do that. So there's a 13 there. Kind of hard to tell with the highlight. Let's try to blow that up. Make it nice and visible for us. There we go. All right, let's try this. We got 2 milliliters. Oh, come on. Right number, sig figs. Come on. And the formula is C3H5N3O9. Wow. All right. And so if we do this, we're going from milliliters to grams, and we can do that with the density. All right. 1 milliliter of C3H5N3O9 is 1.592 grams. And now we have the grams. We're in grams. We can go to molar mass. If I do the molar mass, right, 12.01 for carbon, 1.01 for hydrogen, 1401 for nitrogen, and 16 for oxygen, times by the subscripts, I got 227.11. That's, of course, 1 mole. All right. Then, what? What unit has to go on the bottom? Well, it looks like moles of C3H5N3O9. On top, we want moles of gas. And so we know 4 moles of nitroglycerin here. 12 plus 6 plus 13. I think that's 31. All right, let's see. What do you get? I got 0.109. That's what I got. Yep, that's what I got. All right. If each mole gas occupies 55 liters, right. All right. How many liters of gas are produced? Well, I have 0.109 moles of gas, and we know that 1 mole of gas is 55 liters. It looks like we're going to get 6.0 liters, which is a lot. Think about 2 milliliters of liquid, right, which is a tiny amount. All right? It's like 40 drops on average, between 30 and 50 drops. 40 drops on average. So 40 drops makes 6 Nalgene bottles. That's a lot. How many grams of N2 are produced in this destination? Ooh. So how many grams of N2? So I'm still going to start with my 2 milliliters. Right? It's going to look exactly the same up top. We're going to have 2.00 milliliters of C3H5N3O9. And then it's going to be the same, right? Density. 1 milliliter C3H5N3O9 is 1.592 grams of C3H5N3O9. And then we got to convert 2 grams. 227.11 grams of C3H5N3O9 is 1 mole. And now we're in the molar ratio. So 4 moles of C3H5N3O9. And if we look for N2, N2 is a coefficient of 6. But that's not what it asked, is it? It asked for one more step. 1 mole of N2 is 28.02 grams of N2. All right, so if I do that math, I get 0.589. That is how we do stoichiometry. And with some other complex things in there where you have not just grams, we had density, we had liquid, we had some fun. So hopefully that makes sense. Hopefully you're getting this. If you need to, reach out to me. Do more practice problems. Go to the math lab, all the above. All right? I'm here if you need me. Otherwise, take care, guys. We'll see you next time. Goodbye.